$20,000 and 200. NASA needs 10 people.
Hello and welcome back to Calculus2, Chapter 9, Differential Equations. This is the overview of differential equations. We are not learning the course. There is a 4-credit course that you can take. It will open a lot of doors for you. It's extremely important for electrical, mechanical, civil, all types of engineering. Now, not for computer science. You guys do the linear algebra and discrete. Now, differential equations is the course that gives you all of the physics, all of the engineering. Every formula that exists in physics and engineering is derived through differential equations. And we'll see the example of that tonight. So we are not going to cover anything in depth. I'm going to define this and we're just going to see what it is. You are going to learn only one method to solve differential equations, which is the basic first introductory method, which lives in section 1.1 when you take the course. We go from there. We can talk about exam and stuff later. So what are differential equations? Differential equations are equations which contain functions and its derivatives. So, definition. Differential equation is an equation which contains function, you can call that y, and its derivatives, y prime, y double prime, y triple prime, 3 dots. The notation for that would be f of, now you can have independent variable t, let's go with x. X, y, y prime, y double prime, dot, 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 equal to, well, put 0 there. This is the way to portray functions of multiple variables in Calculus 3. This is called implicit. Eventually you're going to run into this. So, I already said that differential equations give rise to all of our sciences, entire physics, entire engineering, and everything else. So let's take a look at 2 basic examples. And first and most important method to solve differential. Oh, before I go there, solution. This is extremely important. Solution to differential equation is a function, not a number. So let's write that as well. Solution to the differential equation is a function. So when you solve differential equation, you get a function. All equations that you solved so far in your life had a number as the answer. So this is a creature higher up in a hierarchy, right? You solve trigonometric equations, what do you get? You get theta is equal to pi over 2. That's a number. You solve quadratic equation, you get x equals 3, x equals half. Numbers, right? Any equation you solved so far, exponential, logarithmic, whatever, was always x equals a number, theta equals a number. Now, with differential equations, your answers are entire functions. So it's a creature higher than equations that you learned in the past 15 years of math you took. So let's start with the example. I will go with exponential model, biology, and population. That's the simplest thing that we can think of. The way differential equations work is you say the sentence in English, you transfer that into mathematical expression, and it turns out that it's differential equation. The wording that you are saying has to have change in it. Otherwise, you don't get to put the derivative, and you don't have differential equation. So, listen to the wording before you start writing. Just listen. The change in population is proportional to population. Does that make sense? Change population is rapidly dying. The population is decreasing. Does that mean less babies? Does that mean less, right? It means less everything. If the population is thriving, it's going up, right? So the change in population, right? The more people you add, the more babies there will be, because there are more people to make more babies. Oh, you can use rabbits if you're... So the change in population is proportional to population. You have to have population for the population to change and grow. You have a population to change and die, right? So there are factors. Now, we write that sentence and then we transfer it into mathematical. So fit this statement in a single line, right? Don't go 2 lines. The change in population is proportional to population. 1 line. The change in population is proportional to population. The change in population is proportional to population. It's time to transfer this into mathematical expression, and it will work out to be derivative. The change in population, well, that happens in time, so change in population is change in population in time. Is proportional to population. And we just obtained the simplest differential equation known to mankind. dp dt is equal to kp. P of t is population function. dp dt obviously is changing. Constant of proportionality is very important. We'll see when we solve the differential equation in which way it plays the role. So now, what do we have? We have a differential equation. This is a differential equation. We are going to solve this differential equation by using a method, and this is the one you must know and learn: separation of variables. Solve it using separation of variables. Now, what are your variables? Well, clearly k is a constant, so you have 2 variables, p population and t time. It takes time to cook up a baby, 9 months, right? So the population changes in time. It's not instant. So when I am separating variables, I want to have all of the variables of the same kind on one side and other variables on the other side. So what have I done? I divorced dp from dt, used just basic arithmetic to move stuff around, and now you see that your left side is solely p's, which is population variable, and the right-hand side is solely t's, which is time as a variable. It doesn't matter which side k, right? It's just a constant. This is separation of variables, not separation of constants. So k can go on any side. Now, what do you think we are supposed to use to solve this now? Calculus, okay, be more specific. What do we do to both sides? We integrate. You already have dp and dt. That's like your dx. So just stick your integration squiggle, and we are ready to integrate. What is the integral on the left-hand side? You better know it. Thank you. ln absolute p. Great. How about the integral on the right-hand side? Kt plus c, thank you. It's not there for decoration. Plus c. Now, before you ask, how about plus c on the left side? Well, plus c1 on the left, plus c2 on the right, and then you combine c1 and c2 into c. So you just put plus c on one of the sides. Are we agreeing on that? So yes, there are two plus c's, but we combine them into a single and just stick it on one side. Are we done? Well, we can do better. I can get p alone by exponentiating both sides, right? So now p of t is equal to e to the kt plus c. Now, those of you remembering algebra, like both of you in the class, you know that x to the m times x to the n is x to the m plus n, right? So you have this side, split it. So p to the t is equal to e to the kt times e to the c. I'm going to define e to the c as initial population p0 or p0, whatever you want to call it. So now p of t is equal to p0 e to the kt. By any chance, do you remember this formula from your pre-Calculus 1 course, right?
I remember from the last
You remember it from last exam too. See, this doesn't materialize out of nowhere. We started with a sentence that makes sense, that the change in population is proportional to population, and then we just follow the math, and at the end it spits out what is known to be the worst model for population. In differential equations, you are going to have a chapter on this stuff, and you're going to learn the predator-prey models and all other flavors, logistics model, and all of the other ones that actually make better population model, because this population model sucks. You say t goes to infinity, population goes to infinity. Where can you have infinite population? Nowhere, right? The planets are finite, surface area. You can't stick infinite of anything, right? I don't care if you say infinite bacteria. No, right? So we used separation of variables on a differential equation that was separable to calculate this. Now you take this and you do your calculations for population and everything that you did in your pre-calc 1 class. Now, is this so this is the solution, right? And we all agree that this is a solution, and we all agree that this is the a function. So now So I'll just say solution. And this was a solution of differential equation that looked like this. So how do you check your answers for equations? What do? You plug it in, right? So clearly this stuff is going to go for p. You have to take the derivative to plug it in there. So on the side, p prime, which is dp dt, is going to be p0 k e to the kt. So now this goes there, this goes there, and when you plug this in, you see that it works out. This is p0 k e to the kt is equal to k p0 e to the kt. They are the same. So this is the solution to the differential equations, because when you plugged it in, it worked out. This differential equation, dp dt equals kp, is known as linear. It does not contain sine of p. It does not contain p squared. It does not contain p times the derivative. So it's linear. P to the first power, derivative to the first power. So that's what means it's linear. It's also first order because you only have first derivative. And it's separable because you can separate p's from t's and use separation of variables, right, which is integrate both sides to solve it. The second example that I want to work on is the example of kinematic motion. So you start with the idea that acceleration is acceleration of gravity, and you put negative g because it goes down. Then you recall that acceleration as a function of time is the derivative of velocity in time, because acceleration is change of velocity in time. You know that when you push your accelerator pedal, your speed goes up. When you push brake, speed goes down. So acceleration changes speed, velocity. So we are going to replace dv dt for a minus g. Hello, differential equation. I have dv dt, which is a derivative, equal a constant. We immediately separate variables. So dv is equal to negative g dt. Integrate both sides. And we get on the left hand side v of t is equal to negative g is a constant times t plus some constant c, and then we call that constant initial velocity. So now you have that velocity in time is initial velocity minus gt. That's for the free fall. Do we remember from physics? Velocity final is equal to velocity initial plus acceleration times time? Well, that's that equation, except your acceleration is now negative g. Same equation. Again, these things don't come out of nowhere for you to memorize. Every single physics formula can be derived from the differential equation that verbally described what was happening in front of you. Yes?
So any two values, or three values, or whatever, that are related, you can do this with.
Yeah.
And is there anything you can't make an equation like this out of?
No. Okay. You just need to learn that physics in that light. Because now, what is my next thing? My next thing is that velocity, so this is a formula. My next thing is that velocity is change in position in time. So now you have ds dt is equal to v0 minus gt. And what happens? Separate the variables. ds stays alone on the left-hand side, and you have your v0 minus gt, everything times dt. When you integrate, what do we get? On the left-hand side, you get your s of t. On the right-hand side, you get your v0t minus gt squared over 2 plus some constant c. Constant c I'm going to call initial position s0. And when I put this in descending order, I get negative 1/2 gt squared plus v0t plus s0. You remember this formula? Parabolic motion. When you throw something. I know, right? It came right out of these separable differential equations. Entire physics. Entire physics is right there. Now you can go do the momentum, you can derive physics 2, physics 3. Everything comes out of these things. So, studies of differential equation, they are everywhere. And all of your engineering and physics is there. So I hope you will try some of the separation variable problems. And we'll review this again next class. So I'll see you all next week or on Saturday if you're coming.